All right, so we're going to take a look at a sample problem here. It's the last problem. Okay, so I want to find a Taylor polynomial to approximate the sine of x over x accurate to the nearest millionth. So we're going to give that a shot. So I'm going to look at it as a slightly different notation as a function. I'm going to call it the integral from 0 to x of the sine of t over t dt. Now, try as you might with substitution or integration by parts, there is no fundamental antiderivative for this one. This is what's called the SI function. We stumbled across it before in Calc 2. So, so we're going to attempt to find a series solution to it. So, starting off with just the sine of t, sine is an odd function, right? So that means we want the odd powers of x. So the first odd power of x is x. What's the first even power of x? X to the 0. So that would give us a 1 if it were cosine. Sine starts with x, and then it starts alternating. X cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, dot, dot, dot. Down the line, we end up with a -1 to the n. If I start counting with n, this would be the 0th term, first term, second term, third term. So when you're trying to come up with a general nth term or kth term, it's always a good idea to write down what n or k is at each place to make sure you get the notation right. And if -1 to the 0 will be positive, -1 to the 1 will be negative. So I'm good there. So this is either going to be like an n or an n minus 1. So then what do we have? We're going to have an x to an even power. Odd power, excuse me. An odd power is either 2n plus 1 or 2n minus 1 typically. But there can be other versions. And if I plug in a 0 here, I will get x to the first power. If I plug in a 1 there, I'll get x to the third power. So I think I put the right version of an odd number there, divided by that same odd number as a factorial. Oops, let's just do factorial. Plus, dot, dot, dot. All right, so then we manipulate that because we're trying to generate this guy up here. So we have to take that series and divide it by t. Oops, I wrote x's everywhere. So no, those are really t's. T, 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 t. Sine of t over t. So this is going to give me what? 1 minus t squared over 3 factorial plus t to the 4th over 5 factorial minus t to the 6th over 7 factorial. If I need that nth term, it's going to be -1 to the n. Since I'm dividing by a t, I get rid of that 1 right there. So it's going to be t to the 2n. But I'm still dividing by 2n plus 1 factorial. Double check that I wrote that nth term right. If n is equal to 3, then I'm going to get -1 to the 3rd. That's still good. I'm going to get t to the 2 times 3, which is 6. And then I'm going to get 7 factorial on the bottom. So I think I'm still doing good there. Next step is to integrate from 0 to x, sine of t over t, dt, which means integrating this guy term by term. So whenever we do integrate, we're going to have a constant. But here we have boundaries that we're going to plug in. So that constant's going to evaluate out to 0. So we should be all right there. If you weren't sure about that, what's the center of my series going to be here based on what I wrote here? 0. And if I integrate from 0 to 0, I get nothing, right? So the constant's going to be 0 for that reason too. All right, so we don't have to worry about the constant, but I need to evaluate this thing. So what am I going to get? I'm going to get the antiderivative of 1 is going to be a t minus a t cubed over 3 times 3 factorial plus t to the 5th over 5 times 5 factorial. And I think we have a nice pattern going on here. T to the 7th over 7 times 7 factorial. And then our nth term, -1 to n, t to the 2n plus 1 divided by 2n plus 1 in parentheses times 2n plus 1 factorial. And we'll slide this sucker over a little bit. And then this goes on forever, and we have to evaluate it from 0 to x. Now, fortunately, every term is a power of t, so plugging in the second boundary of 0 means we're subtracting a whole bunch of zeros, so that's cool. And so really, this just reevaluates with x up there. And you always don't, it's not a good idea to jump straight to x's in there and assume the n's going to be 0. Think hard about it before you do so. Okay, so we know now that this is just going to be a bunch of x's, so I'm just going to rewrite that on the next page. So our function, let's call it capital F of x, which equals the integral from 0 to x of the sine of t over t is equal to that, I'll just write it as a summation first, the sum as n goes from 0 to infinity of -1 to the n times t to the 2n plus 1 over 2n plus 1. Sorry, I'm ditching the t's now. First I was stuck on x, now I'm stuck on t. X, there you go, 2n plus 1 factorial. So we could, for example, create a Tailor polynomial based on this infinite series. And so we could say our function is approximately equal to, let's say we're going to go up to the 5th degree Tailor polynomial. And so that would be x minus x cubed over 3 times 3 factorial plus x to the 5th over 5 times 5 factorial. And if x is a positive number, right? So we should think about the interval here. What's the interval of convergence? Let's play around with that. And we'll talk about error. So this example is going to review pretty much everything we've done. Interval. We would have to apply the ratio test. And so the ratio test says plug in an n plus 1 here for this stuff. So I'm going to write it down below. Because of the absolute value, I can ignore the alternating part. So I'm going to have an x. If I replace n with n plus 1, that's going to give me 2n plus 2 plus 1, which I believe is 2n plus 3. Divided by, and nice thing, the same thing all over the place. So there'll be a 2n plus 3 down here, and a 2n plus 3 factorial, times the reciprocal of the nth term, 2n plus 1, 2n plus 1 factorial over x to the 2n plus 1. All right, how is this going to clean up? It's usually a good idea to be safe, especially with factorials that aren't just n. So 2n plus 3 is bigger than 2n plus 1. So I want to think about what it looks like as a factorial. So if I rewrite that as a factorial, it'll be 2n plus 3 times 2n plus 2, and then 2n plus 1 is going to come next. So I'm just going to say the remaining terms are essentially 2n plus 1 factorial. So that's going to help me in terms of cancellation. I can say, oh, the 2n plus 3, I'm stuck with those 2 front terms, but then this stuff goes right there. what happens with the x's? What's 2n plus 3 minus 2n plus 1? It's just 2, right? So that goes into that, x squared times. And these guys don't divide into each other. We're just stuck with the ratio there. So let's clean up. What do we have then? We have the absolute value. We have an x squared in the top. And we have a 2n plus 1 at the top. In the bottom, let's see, I've got a 2n plus 3. I've got another 2n plus 3. And I have a 2n plus 2. Did I get everything? I think so. 1, 2, 3 things not crossed out there. 2 things, yeah, that looks right. Okay, so if I were to multiply out the denominator, I would have a cubic polynomial on the bottom. I have a linear polynomial on the top. So when I take the limit as n goes to infinity, the denominator is going to crush the numerator, getting bigger and bigger and bigger. And so this fraction is going to go to 0. You guys agree? Mm-hmm. So what I can say is as n goes to infinity, this goes to 0. This being that whole thing there. Ratio test says, all right, you are less than 1. So what's my interval then?
Infinity.
It's all real numbers. So the radius is infinite, and that means all real numbers. So, and usually I'm more concerned about the interval than the radius. And so here I can say the interval is all real numbers. Okay, so that's good there. Next thing is we're going to look at how accurate, say, our fifth degree polynomial approximation of this interval is going to be. So a couple of ways to think about it. The first way to think about is Taylor's remainder theorem, which is really Lagrange's remainder theorem. And what it says is that the actual error, and remember the actual error is the difference between the function and any approximation I make of the Taylor series. That's always going to be equal to the nth derivative evaluated at some magic number z divided by n factorial times x minus the center. I'm just going to go with the center of 0 here. So x to the, let's see, what did I do wrong here? And that should be an n plus 1, sorry. The next derivative, x to the n plus 1. Now, the magic number z is generally a problem, so what we say instead is, well, it's going to be less than or equal to some max value, n, times x to the n plus 1 over n plus 1 factorial. And remember, because x can be any number here, we better put absolute values around everything to be safe. For our function right here, taking derivatives of this is going to be a mess. Remember we played around with the sign of something squared? We got nasty derivatives. It got out of control fast. Here we're going to have the quotient rule repeated over and over again. It's going to get nasty fast. So what we're going to find here is that this is going to be a wicked tough problem to solve. However, I have an alternating series here. So that means I can use the alternating series remainder test instead. So as long as it strictly alternates, I can use that instead, which is easier. So I'm gonna, and I meant to mention that in class the other day, but it just slipped my mind. And so we could have done that on the sine squared problem, the sine of x squared problem, instead of that nastiness we get stuck in. So instead, let's try the alternating series. Alternating series remainder. Okay. And so alternating series test says that your error is going to be less than or equal to your next term in line. So I stopped at the 5th degree. Alternating series test says to go grab the next term in the sequence. Now Taylor's series says to find the next power of x. Those are two slightly different things. So if I look at this series right here, if I went to the next available term, because it's got to be strictly alternating, right? Because the next power of x has a 0 coefficient. So that doesn't count for the alternating series test. For alternating series, I have to say, well, the next alternating term would be negative x to the 7th over 7 times 7 factorial. Okay, so that which term to get is always tricky business. With Taylor's theorem, it's the next power of x. With the alternating series test, it's the next non-zero strictly alternating term. Okay, now there's a catch here though, because here I said x can be any real number, but if x happens to be a negative number, what's going to happen? Let's see. Oh, that's okay, actually. I'll have a negative times a negative, which is positive. Yeah, it just switches the alternating. Oh, we're good. So sometimes with alternating series, you can cancel out the alternating stuff, and you have to just say, all right, we're only going to look at positive x or only negative x. In this case, when we plug in a negative x value, we just switch where the alternating sign is. Okay, instead of positive negative, it goes negative positive. All right, cool. So that right there is our key. So our error is going to be less than or equal to, I need the absolute value because I have an x here. So it's going to be x to the 7th over 7 times 7 factorial. Now, as x gets bigger, can you see that this is going to change as we move on? But this is our estimate of what our error is going to be. So then we'll have to say, okay, well, which x values are we interested in? We have to narrow it down because this is an error term for any x value. So we might say, let's just try x values between -1 and 1. If I do that, if I restrict myself to only those x values, well, then I can say, hey, the biggest x can be is 1, right? So that's my worst case scenario for error. So then on this interval, my error is going to be less than or equal to 1 over 7 times 7 factorial. What is 7 times 7 factorial? Let's check it out. Calculators, please, help me out. 7 times 7 exclamation point. It's 35,000. And so if I divide by 35,000, I get 1, 2, 3, 4 places of accuracy. If I divide by 35,000, so 0, 0, 0, 0, let's call it 3. So this right here is about 0.00003. So on the interval from -1 to 1, I'm at least this accurate. Now this is the worst case scenario. That's my error at the endpoints. Okay. Other thing to remind myself is, did I have a center of 0 this whole time? Double check. Yep, I have powers of x, so the center is 0. Make sure we're centered in the right spot. If somebody said, well, I really need you to get up to x equals 2 or 3, then I would have to reevaluate this. And I said, okay, if I was interested in x values up to 2, then that's going to change this. So my error would then become, toward the endpoints, as bad as 2 to the 7th over 7 times 7 factorial. So if I reevaluate that scenario, I throw a 2 to the 7th in my numerator. Now I only have 2 decimal places of accuracy. So the error is going to change, and we know that. The farther you move from the center, it separates, and you need more terms to get it to cut closer. So then you would, if somebody said, hey, I need 1 million accuracy, you would just have to say, okay, we just need more terms. That's all. Now, another problem I have here is analyzing that million. So I have to do 2 things here. I have to say, okay, how far out do we want to go for x? And I left that as kind of an open problem in that on that exam. And then how many terms do I need to make that happen? So let's just restrict ourselves. Let's stick with this interval right here and see how we can get more accurate. So are we to the nearest millionth yet? Well, tenths, hundreds, thousands, 10,000s, no, I need 2 more decimal places of accuracy. So then we would have to bump out our factorial, okay? So now we have to try and test some stuff. Because what I want to know is my next term is going to look something like x to the 2n plus 3, right? The next one after where I stopped. And according to my series, I'm stopping at 2n plus 1. So what's the next odd number after 2n plus 1? It's 2n plus 3, okay? So that's why I'm stating it that way. So my error is going to look like this, 2n plus 3 times 2n plus 3 factorial. Now, we're also adding the restriction that x has to be less than or equal to 1. So now my error can be rewritten as 1 over 2n plus 3 times 2n plus 3 factorial. If somebody later tells me they want it to be less than some number a, then I would have an a to the power 2n plus 3 complicating things. But let's keep it simple. And somebody says, well, I need this error term here, your endpoint struggles, to be less than or equal to a millionth. So 0.10ths, hundredths, thousandths, 10,000s, 100,000s, millionths. So that would be to the nearest 1 millionth right there, which gives me 1, 2, 3, 4, 5 decimal places of accuracy. You can't solve algebraically a factorial equation. So the only choice is like we had to do a couple of days ago in class, pick some numbers for n and guess to see what happens. So let's do that. We know that if, let's see, if n was 2, then we're going to get 1 over 7 times 7 factorial. And that leads to an error term of about, what was it, 0.12343. So n equals 2 isn't good enough. So then I have to try n equals 3, which is going to be 1 over 9 times 9 factorial. Let's calculate that. And I get 6 decimal places of accuracy. Yeah, so it looks like if I let n equal 3, then I'll get 0.12345 What was next? 3, roughly. Which is better than what I was asked to do. So if n equals 3, where does that put me? Well, looking back at my polynomial over here n equals 0, let's see, 0, 1, 2, 3. I would have to go up to the 7th term to be that accurate. So I would need all of this right here. Because what term is after the 7th power? It would be the 9th power, which is the error approximation that we just tested. Right here. So here's one possible answer for that test question. Oops. So on the interval, x is less than or equal to 1, t, let's see, 7th polynomial, the 7th power of x, which equals x minus x cubed over 3 times 3 factorial plus x to the 5 times 5 factorial, minus x to the 7th, 7 times 7 factorial. This polynomial is accurate. To about 0.123456 So 1, 2, 3, 4, 5, 6 decimal places. If I'm told to expand my interval that I'm looking for x values, then I'm going to have to add more terms. right? Because we know that our error is going to change as we move out with x. Does that make sense?
Mm-hmm.
So it's a relatively complicated problem, and we have to look at it with different parameters going on at once. We have to both consider what is x and what is n at the same time. And that's about the hardest kind of problem we look at. Here we got lucky and the series alternated, so we could use the alternating series test instead of Taylor's remainder theorem. With Taylor's remainder theorem, you have the struggle of trying to find a maximum bound on some nth derivative of that function.
So when you chose to test Taylor polynomial, was that kind of arbitrary?
Yeah, I just said, hey, let's try the fifth one to see what it's like.
Okay.
Yeah, so I said, okay, so I was working my way up to that other question that was on the test. So if I had a fifth Taylor polynomial and I restricted myself to the interval from -1 to 1, then I would be accurate to about 4 decimal places. In the center of the interval, I'm going to be way more accurate than that. So this is a worst case scenario on the error, right? And it says error is less than or equal to. Yeah. And then I look back at the question that said, no, I need you to be within a millionth. So then I said, oh, we better go out farther with the number of terms we're looking at. And it turned out that just going out one more term was good enough if we stay on that interval. If somebody says, I need you to be on that interval between -2 and 2, then I would have to see what happens adding another term on to that error. But here we're lucky the alternating series says just test the factorial divisors and see where you end up. All right, so I need to wrap things up here because I have to pay a visit to some high school students, try and get them interested in more math. If any of these problems prove difficult, what did we do there? How come there's only one question now? Where did the other ones go? What? Okay, computer's glitching out seriously here. I have no idea what's going on there. I must have a strange electromagnetic field today. All right, let's make you go away. So there is a sample test. You'll notice that this is a lot like that quiz. Oh gosh, look at those quizzes again. I will scan them later today and get them to you. The test will come in basically 4 parts. They'll be looking at regular sequences. That's just limits. And I'll put a note at the top. These are regular sequences, just do limits. The next page will say, okay, these are series. Think about all the different tests we've had. Then the next page after that will say, okay, now we're playing with power series. We have x's involved. Here we're interested in intervals of convergence testing endpoints. And then the 4th page will say, okay, now we're going to generate and use some Taylor series and take a look at errors. What I usually do with this is I let you pick a few problems to take home. So I'll say of these problems right here, pick 5 to do in class and 2 to take home. And then with the Taylor stuff, I'll say pick 2 to do in class and pick 1 or 2 to take home. And that's what I'll give you on Tuesday. All right? Okay. Well, have fun, do good math, stay in touch.